Study non-linear space. So first of all, we will study the definition of vector space. A vector space over a field K is a non-empty set X of elements X, Y and so on together with two algebraic operations. These algebraic operations are called vector addition and multiplication of vectors by scalars, that is by elements of K. Because K is a field, its elements are called scalars and elements of X are called vectors. So X, Y and so on are elements of X. We also call vector space to be a linear space. So what is this algebraic operation of vector addition? Vector addition means it associates with every ordered pair X, Y, this is small x, of vectors, a vector X plus Y called the sum of X and Y, such that vector addition is commutative, means X plus Y equal to Y plus X, and associative means X plus Y plus Z is equal to X plus Y plus Z. Further, there exists a vector 0, we call it a 0 vector, and for every X there exists a vector minus X, such that for all vectors we have X plus 0 equal to X and X plus minus X equal to 0. And what is multiplication? So multiplication by scalar associates with every vector X and scalar alpha a vector alpha X. Alpha X is the product of alpha and X, so that for all vectors X, Y and scalar alpha beta we have alpha into beta X equal to alpha beta into X, and 1 into X is equal to X. And it also obeys distributive laws, means alpha into X plus Y equal to alpha X plus alpha Y, and alpha plus beta into X is alpha X plus beta X. From this definition we see that vector addition is a mapping from Cartesian product of X with X to X, where multiplication by scalar is a mapping of Cartesian product of K with X to X, because here we are multiplying it by a scalar alpha. So it is a mapping from Cartesian product of K and X to X. Here this K is called the scalar field of vector space X. X is called the real vector space if K is equal to R, and complex vector space if K is equal to C, means set of complex numbers. Now what is subspace? A subspace of a vector space X is a non-empty subset Y of X, such that for all Y1, Y2 belonging to Y at all scalars alpha beta we have alpha Y1 plus beta Y2 belonging to Y. Hence Y itself is a vector space, and the two algebraic operations being those induced by X. A special subspace of X is a improper subspace Y equal to X, and every other subspace of X which is not equal to 0 is called the proper subspace. Now what is linear combination? A linear combination of vectors x1, x2 and so on up to xm of a vector space X is an expression of the form alpha 1 x1 plus alpha 2 x2 plus dash 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 alpha m xn, where these coefficients alpha 1, alpha 2, alpha m are any scalars. So this expression is called the linear combination of vectors x1, x2 up to xm. Now span. For any non-empty subset M of X, the set of all linear combinations of vectors M is called the span of M, and we write it as span M. This is the set of all linear combination of vectors M. Obviously this is a subspace Y of X, and we say that Y is spanned or generated by M. Now linear independence. Linear independence of given set M of vectors x1, x2 up to xr, where r is greater than or equal to 1 in a vector space X are defined by means of this equation. What is this equation? Alpha 1 x1 plus alpha 2 x2 plus alpha x are equal to 0. Here these alphas are scalars. If this expression hold for alpha 1 equal to alpha 2 equal to alpha r equal to 0, means all the alphas are 0, then the set M is said to be linearly independent. If M is not linearly independent, then we say that M is linearly dependent. It means this expression holds for some r tuples of scalars, not all 0. In case of linear independence, all the alphas are zeros. Alpha 1, alpha 2, alpha r all are equal to 0. But in linear dependence, all the scalars are not 0. If M is equal to x1, x2 up to xr is linearly dependent, at least one vector of M can be written as linear combination of the others. Means we can simplify this expression because one of the alphas is not equal to 0. Suppose we say that alpha r is not equal to 0. If alpha r is not equal to 0, then we can shift the other terms to this side, and if we divide by alpha r to this side, then we will get minus alpha 1 upon alpha r minus alpha 2 upon alpha r minus and so on are the coefficients of x1, x2 and so on. And if we write minus alpha 1 upon alpha r to be beta 1, minus alpha 2 upon alpha r to be beta 2 and so on, then we can write it as xr equal to beta 1 x1 plus beta 2 x2 plus beta r minus 1 xr minus 1, where beta r is equal to minus alpha j upon alpha r. J may be any number from like 1, 2, 3 and so on. So we if M is the set of linearly dependent vectors, then we can write or express xr as the like this, which is a linear combination of these elements. Here x1, x2, xr minus 1 are scalars, and beta 1, beta 2, x1, x2, xr minus 1 are the vectors, and beta 1, beta 2, beta r minus 1 are the scalars. Now finite dimensional vector space and infinite dimensional vector space. How do we find the dimension of a vector space? A vector space X is said to be finite dimensional if there is a positive integer n such that X contains linearly independent set of n vectors, whereas any set of n plus 1 or more vectors of X is linearly dependent. So in this case, n is called the dimension of X, and we write n is equal to dimension of X. It means X contains linearly independent set of n vectors. So if X is equal to singleton set 0, it is a finite dimensional and dimension of X is equal to 0. If X is not finite dimensional, it is said to be infinite dimensional. In this case, it may contains linearly independent set of vectors which is greater than or equal to n. Now basis. If dimension of X is equal to n, a linearly independent n tuple of vectors of X is called the basis for X, or we also say a basis in X. If E1, E2 and up to En is a basis for X, then every X belonging to X has a unique representation as a linear combination of the basis vectors. Like we can write X equal to alpha 1 E1 plus alpha 2 E2 plus alpha n En. Hence, if B is a basis for X, then every non-zero X belonging to X has a unique representation as a linear combination of finitely many elements of B with non-zero scalars as coefficients. For example, a basis for Rn is E1 equal to, here first element is 1, other elements are 0. E2 equal to second element is 1 and all other are 0, and En all other are 0, nth element is 1. This is sometimes called canonical basis of Rn. If X is any vector space, not necessarily finite dimensional, then B is a linearly independent subset of X which spans X. In this case, B is called the basis, or in particular we call it as a Hamel basis for X. So every vector X not equal to 0 has a basis. Now dimension of a subspace. Let X be n-dimensional vector space, then any proper subspace Y of X has dimension less than n. Suppose n is equal to 0. In this case, X is equal to singleton set 0 and has no proper subspace. If dimension of Y equal to 0, then Y is equal to singleton set 0 and X is not equal to Y, means dimension of X is greater than or equal to 1. So clearly dimension of Y is less than or equal to dimension of X, which is equal to n. If dimension of Y is equal to n, then Y would be a basis of n elements, which would also be a basis for X, since dimension of X is equal to n, so that X is equal to Y. So it means any linearly independent set of vectors in Y must have fewer than n elements, or we can say dimension of Y is less than n. Now how do we define a norm? A norm on a vector space X is a real valued function on X whose value at X belonging to X is denoted by norm of X. We write like this. This side we write 2 lines, this side also we write 2 lines, and we call it norm X. And this has a properties like norm of X is greater than or equal to 0. Number 2, norm of X equal to 0 if and only if X equal to 0. Norm of alpha X equal to modulus of alpha into norm of X, and norm of X plus Y is less than or equal to norm of X plus norm of Y. And this is also called the triangle inequality. Here X and Y are arbitrary vectors and alpha is any scalars. So what does these properties states? What is the meaning of these properties? So first properties state that all vectors have positive lengths except the 0 vector, which has length 0. And second property states that all the vectors have positive length except the 0 vector, which has length 0. And third property means when a vector is multiplied by a scalar, its length is multiplied by absolute value of the scalar. And fourth is the triangle inequality. It means that length of one side of a triangle cannot exceed sum of lengths of other sides of a triangle. So these definitions of a norm are suggested and motivated by the length modulus of X of a vector X in elementary vector algebra. So that in this case we can write norm of X equal to modulus of X. A norm on X defines a metric D on X, which is given by dxy equal to norm of X minus Y, where xy belongs to X. Clearly it is a metric because it satisfies all the properties of a metric. Because norm of X minus Y is always greater than or equal to 0. Norm of X minus Y equal to 0 if and only if X minus Y equal to 0 means X equal to Y. Norm of X minus Y is equal to norm of Y minus X, and it also satisfies triangle inequality, means it satisfies all the properties of a metric. And this is also called the metric induced by norm. So norm space just defined is denoted by X together with norm or simply by X, because sometimes while writing we omit this notation. So norm space is a vector space with a metric defined by a norm which generalizes the length of a vector in the plane or in three-dimensional space. So in a norm space, we can also define and use infinite series. A mapping from a norm space X into a norm space Y is called the operator. And a mapping from X into a scalar field R or C is called the functional. Also, the norm is always continuous, means a mapping from X to norm X is a continuous mapping of this norm space which is defined with X together with some metric defined by norm or induced by norm into R. So this norm is always continuous. Thank you.